In the Z module of degree D homogeneous symmetric functions, we've looked at the transition matrices relating various bases, mostly relating bases to the monomial basis. Now I want to look at transition matrices relating bases to the power sum basis. And this involves important work of Frobenius that relates symmetric functions to representations of the symmetric group. So Frobenius showed that Sn characters appear if we express symmetric functions in terms of power sums. In particular, we can write the Schur function as 1 over n factorial, the sum of all permutations in the symmetric group, chi lambda of W times P sub cycle type of W. And we can write the homogeneous symmetric function H lambda as 1 over n factorial, the sum of all permutations in the symmetric group, induced sign character indexed by lambda of W, P cycle type of lambda, cycle type of W. And the elementary symmetric function is 1 over n factorial, sum over all permutations, induced sign character of W, P cycle type of W. Now this isn't expressed exactly as transition matrices because, well, P is indexed by partitions rather than permutations. We'd like to collect together all the permutations that have the same cycle type, and then that collection will give us the right coefficient in the power sum expansion. So let's look at the Schur case first, and then everything else is going to be similar. Now we know that chi lambda is constant on conjugacy classes. So we could look at conjugacy classes, so summed over mu. Chi lambda on some typical element of that conjugacy class. So I'm writing C mu for the conjugacy class. The conjugacy class of permutations having cycle type mu. So then we need the number of permutations in there because we're taking a bunch of terms of the sum and adding them together, that many, P sub mu. Alright, now we need to think about what is the conjugacy class size. Well, one way to get a permutation of cycle type mu is to permute 1 through n in any order we want, and then cut off the first lambda 1 letters, the next lambda 2 letters, mu 1 letters, the next mu 2 letters, the next mu 3 letters, etc., and call those the cycles. But of course we're overcounting if we do that, because the first mu letters, if that's a cycle, we could choose any one of those mu letters to start the cycle. So we have to divide by mu 1. And then for the next mu 2 letters, we could choose any one of those to start the cycle. So we have to divide by mu 2, etc. And then we have to realize that if there's 2 cycles of the same size, or maybe k cycles of the same size, that the k permutations of those cycles amongst themselves are going to yield the same permutation, so k factorial times. So we need some notation for the multiplicity of each part in mu. So I'll write multiplicities. Each one of those is going to be factorial. So let's let mu be alpha 1 1s, alpha 2 2s, etc., alpha n n's. So I guess the size of the conjugacy class is going to be n factorial over. Now so here alpha 1 means multiplicities, but if we just treat these as numbers, then 1 to the alpha 1, 2 to the alpha 2, up to n to the alpha n. If any one of these multiplicities is 0, then we've got something to the 0th, which is just 1. This is the product of all the parts. And then for every multiplicity that's greater than 1, we need that factorial. Of course, 1 factorial is 1, so it doesn't hurt. 0 factorial is 0, so it doesn't hurt. So we can just multiply by the factorials of all of these multiplicities. Let's call this number z mu for short. Alright, so we want to continue with this until we get something nicer here for the coefficient of p mu. And we've got this n factorial in front here, which could be incorporated. So we have S lambda equal to a sum over all partitions mu of n, chi lambda of any permutation in that conjugacy class consisting of permutations of cycle type mu, size of the conjugacy class over n factorial p mu. Now if the size of the conjugacy class is n factorial over this n factorial and that n factorial are going to cancel. And we'll get 1 over actually I wanted to call this denominator z mu. So this numerator n factorial and that n factorial are going to cancel, and we'll get p mu, and all of this is over z mu. So the coefficient of p mu is the irreducible character evaluated at anything in that conjugacy class of permutations of cycle type mu, all divided by z mu. So similarly, h lambda is a sum over all partitions of n, eta lambda of c mu over z mu p mu, and epsilon is the sum over all partitions mu of n, epsilon of c mu over z mu p mu. Now it's not often that we really want to express different bases in terms of the power sum basis, because the monomial basis is the most natural thing to work with. But these formulas of Frobenius point out something interesting, and that is, so if we let T of Sn be the trace functions of Sn, so that's all of the functions theta from Sn to, say, the integers, such that theta of uv equals theta of vu. These are also the class functions. This has dimension equal to the number of partitions of n. And some bases are the irreducible characters, the induced trivial characters, and the induced sign characters. Now, dimension of homogeneous symmetric functions of degree n is also the number of partitions of n, and some bases are the Schur functions, the homogeneous symmetric functions, and the elementary symmetric functions. Now, these formulas of Frobenius show, well, you have to look at it, work with it a little bit. They show that the transition matrices relating these three bases of the symmetric function z module are exactly the same as the transition matrices relating these three character bases of the trace space. I'll let you work out the details of that for homework. All right, well, we have at least three bases of the trace space that correspond to three bases of the symmetric function space, but we know more bases of the symmetric function space. And these are really the only three bases we've talked about for the class function space. So it seems like, since we're expressing everything in terms of power sums, that we should be able to find pretty easily a basis of the trace space which corresponds to the power sum basis of the symmetric function space. So let me define this, give this correspondence a name. So we've got these trace space bases. And homogeneous symmetric function bases. Call this the Frobenius characteristic map. So we're going to map any trace function theta to a sum over all partitions mu of n, theta of the conjugacy class indexed by mu, times p sub mu all over z mu. So let's suppose psi lambda in the trace space satisfies characteristic of psi lambda is p lambda. So it's natural to ask what function psi lambda satisfies that. Is going to get mapped to the power sums, just the way that irreducible characters got mapped to Schur functions, induced trivial characters got mapped to homogeneous symmetric functions, and induced sign characters got mapped to elementary symmetric functions. So if p lambda is the characteristic of psi lambda, which is the sum over all partitions mu of n, psi lambda, conjugacy class indexed by mu, p mu over z mu, then the equation p lambda, if we express the power sums in terms of the power sums over z mu to get this part here, then I guess we have z lambda p lambda over z lambda. So this equation implies that, well, for any partition mu that's not lambda, we're not going to have a sum at, we don't have a sum at all. The sum has one term. So for any mu partition that's not lambda, that coefficient has to be 0. So 0 if lambda is not mu. And if lambda is mu, then I guess it's just z lambda. So this is sort of an indicator function on a conjugacy class. It's basically 1 or 0 if these are equal or not equal, except it's multiplied by this constant z lambda. Alright, that's a pretty simple function. Now let me point out, this is the first one that's not a character. So psi lambda is a trace, but not a character. since it's not a non-negative integer linear combination of irreducible characters. And the Sn characters, recall, are the elements of the trace space which are non-negative integer linear combinations of irreducible characters. All right, now the next logical thing to look for is a trace space basis which is analogous to the monomial basis of the symmetric functions. So let's suppose phi lambda in the trace space of Sn satisfies characteristic of phi lambda is the monomial symmetric function. Then what function is phi lambda? Well, this one's not as easy to see. In fact, figuring it out would be sort of complicated, but I'm just going to put the formula up on the board just so that you know that there is a formula. And I don't expect that we're going to use exactly that formula very much, although we will come into this, we will see this function again. So phi lambda of W is -1 to the n minus length of the partition lambda times sine of W times a number which I'll call R sub W R lambda of W, where R lambda of W equals the number of ways to cut the cycles of W into chains of cardinalities lambda 1, lambda 2, etc. So for example, let's compute phi 211 of 1423. So this is -1 to the 4 minus 3 parts in phi times the sine of 1423. There's two inversions here, 4, 2, and 4, 3. So this is even, it's an even permutation, so this is just 1, times the number of ways to cut. If we write this in cycle notation, 1, 1 is a cycle. And then 2 goes to 4, 4 goes to 3, 3 goes to 2. So number of ways to cut this into chains of cardinalities two, 1, 1. So there's 3 ways to do that because, well, this is already a singleton. We just need to choose a singleton over here. So we either choose the 2, the 4, or the 3. So we either got 1, 2, and then we've got 3, 4, or 1, 3, and then we've got 2, 4, or 1, 4, and we've got 2, 3. So 3, oops, I forgot the negative 1. It's negative 3. Now there's two things that are worth noting about this. This formula maybe isn't so important. The formula is similar to the expression for PD in terms of the elementary symmetric functions. Which we used with Ganttmacher's theorem. And the more important thing to notice here is recall that Schur functions, elementary symmetric functions, homogeneous symmetric functions, and power sum symmetric functions all belong to the non-negative integer span of the monomial symmetric functions. So these functions, whatever they mean, they're not characters because they're not non-negative linear combinations of Schur functions. But the functions phi lambda, whatever they are, satisfy that the irreducible characters, the induced trivial characters, the induced sign characters, and even these sort of indicator trace functions all belong to the non-negative integer span of these monomial traces, let's call them. Monomial traces, just because they're related to these other traces the way that monomial symmetric functions are related to Schur functions, homogeneous symmetric functions, elementary symmetric functions, and power sum symmetric functions. So that means that if phi lambda of G is greater than or equal to 0 for some element G of the group algebra of the symmetric group, then chi lambda of G is greater than or equal to 0 also, epsilon lambda of G is greater than or equal to 0 also, and all of these other evaluations are going to be non-negative just because all of these functions are non-negative linear combinations of the monomial traces. So if we ever want to prove that something is non-negative, it could suffice to prove it for monomial traces first. The end.